We're going to look at a mass spring system that's oscillating. We're going to take a look at the energy of it. So this is section 15.3, and we're going to talk about the energy of a I'll just call it SHM, simple harmonic motion. Of simple harmonic motion for a mass spring system. So this is just looking at the energy considerations of what's happening. Because last time we talked about we described the motion, right? So just to review, here's our mass spring system. Put this on wheels. There's no friction in the system at all. And here's the equilibrium position. And if we pull this thing out to a certain amplitude, this thing is going to oscillate back and forth. Once I release this thing's going to oscillate back and forth. And we said that the motion here for this mass spring system, our position x, if we start right here and just release it, x is going to be equal to a, so this has some maximum value of a, times the cosine of omega t, and where omega is equal to the square root of the spring constant divided by the mass. And so this equation right here describes the motion of this object as a function of time. Yes? Yeah. Oh, okay. That's a great question. When do you use cosine or when do you use sine? If at t equals 0, if the object starts here but it has some velocity, then I would use sine. Because at t equals 0, the sine of 0 is 0. And so its position is 0 here. And then, and it'll be the same equation, it just starts in a different place. Okay, so, but usually I'd say that most problems, they start out here, but not always. And we'll go over a couple problems where you want to start with a sine because the object's right there. All right, but look, if I pull this thing out here, I've done work on it, right? So I take this and I'm about to release it. So I release it and then it goes back and forth. Well, where is the energy in here? How much mechanical energy is there in this system? Well, we don't have to worry about gravitational potential energy in this problem, but the object's going to be moving, so there's kinetic energy. So the amount of energy will be shared between the elastic potential energy in the spring plus the kinetic energy due to the motion of the object. Well, one of the things that we can see right away is that the sum of these two is going to be equal to, well, think about it when it's way out here. How much energy is in a stretched spring? Well, it's 1/2 kx squared, right? 1/2 the spring constant times x squared. Well, x, when it's over here, at its maximum value is a. So it's 1/2 ka squared. And when it's at its maximum displacement, it doesn't have any velocity, right? We've stretched the spring as much as it's going to stretch. So as long as it's out here, it's not going to be moving. So it has no kinetic energy at that point. So all of the energy is in the stretched spring at this point right here, or at this point over here, negative a, but it gets squared, so it doesn't matter. Okay, but what if it's in between? What if it's somewhere in between here? Well, it's going to be shared. Or if it's right in the middle, right? What if it's right in the middle? It's all kinetic energy. If it's right in the middle, the spring isn't stretched or compressed, so all the energy is in the kinetic energy. So, let's kind of explore some spot in the middle. We'll just call that X. Well, we know then that the total energy in your system at this point X is going to be the elastic potential energy, which is 1/2 K X squared, right? Plus 1/2 M V squared, the kinetic energy. Right? Simple. But we have equations for these guys. We just said that X is equal to this. We'll start it here and release it. So we'll say that X is equal to, well, what is V? Well, if X is equal to this, we'll have V is equal to the derivative of this, which is negative A omega sine omega t. You agree with that? You have to use that chain rule again, and so you have an A omega, by the way, is the velocity, the maximum velocity of the velocity of the object. We'll talk about that here in a minute. But well, now I've got an equation for velocity I can put right here. And and we've got an equation for, position. To time, yes. Yeah. Yeah, I mean, velocity is dx dt, right? So now I can substitute these in, and we're going to get something kind of cool. We're actually going to go in a big circle here. But E, the total mechanical energy, is equal to 1/2 K X squared. Well, what is X? It's A cosine omega t, but we got to square it, so that's going to be A squared cosine squared omega t, right? Plus this squared, 1/2 M V squared. Well, that's going to be, the negative gets squared away, so this becomes A squared omega squared times the sine squared omega t. Well, this is all kind of ugly. I wonder if there's some way I can clean this up, and of course there is, because we know what omega squared is, right? Omega squared is K over M. So let's substitute that in and see what happens. Well, we said that omega squared is just K over M times sine squared omega t. I just love little things like this. Look what happens to the M. And look what I'm left with. I got a 1/2 K A squared and a 1/2 K A squared in both terms. Let's factor those out. And what's left is cosine squared omega t plus sine squared omega t, which is like the most important trig identity in the world. Cosine squared plus sine squared is 1. So what we're saying is that 1/2 K, you end up with 1/2 K A squared. Well, darn tootin' you should. I mean, that's what we started with, right? We said, hey, look, if I pull this thing all the way out, how much work did I do? Well, I did 1/2 K A squared. Well, what this is saying is that no matter where I am in here, I've got the same total mechanical energy, 1/2 Ka squared. Okay, so that's pretty cool. Now, let's take a look at this thing graphically. Let's graph the energy as a function of time, and we're going to graph the energy as a function of position. Let's graph it as a function of position first. And by the way, this is on figure 15.10 on page 462. Figure 1510. And this is a really good one to study. I'm going to exaggerate my mass spring system. So here's my mass at the equilibrium point. There's x equals 0 right there. And here's my spring. And let's let it oscillate from here to here. So I'm going to pull this thing out like this and release it, and it's going to oscillate it back and forth like this. Well, this is x. So if I were to graph the energy as a function of x, so here's energy. Well, I'm actually going to put 3 graphs on here as a function of x. Here's, oh, you know what? Hold on a second. I'm going to change this a little bit because there's no need to put that axis there. That's a little bit deceptive. I'll just put it right over here. But here's energy. Now, actually, my origin is right here. This is where x is equal to 0. And if I look right here, this is negative a. And over here, this is positive a. So, because this is x, this is the position as a function of time. Now, if I graph the total mechanical energy as a function of position, well, we said over here, look, the total mechanical energy is a constant. It's 1/2 Ka squared. So I'm just going to, on my graph, I'm going to say, hey, this is 1/2 Ka squared. And the total mechanical energy here is a constant. It doesn't change. The total energy, so we'll make this is E. But now let's draw a separate graph for the kinetic energy. What is the kinetic energy at negative A and at A? 0. But what is the kinetic energy at the center? At x equals 0. It's 1/2 Ka squared, so it's like this. But it's not a straight line, right? It's got to be some kind of a curved thing like this. Now we'll see why here in a second. Because what is the potential energy function? Well, the potential energy function, for elastic potential energy, is 1/2 K x squared. So this is a function of x. So when x is 0, we have 0 energy. So therefore, all of the energy has to be kinetic energy. We have 0 potential energy, so all of my mechanical energy has to be there. Now, here is 1/2 kx squared is the potential energy function. So that's going to be a parabola like this, isn't it? Let me make it a kind of a thick. Well, I'm going to show you that here in a second. So this right here is U, potential energy is a function of X? Well, we need the kinetic energy as a function of X. Well, here's what we know. We know that E is equal to K plus U, right? So what is K as a function of X? The kinetic energy as a function of X is just going to be E minus K. I'm sorry, minus U. Now this is a function of X, not a function of velocity. It's a function of position. So K is equal to 1/2 KA squared minus 1/2 KX squared. Well, this is just a shift in the energy up to here, and this is minus 1/2 kx squared. So that's an upside down parabola, just like this one. So there's my potential energy, or my kinetic energy function, K. So there's K. So this is the total energy. This is the kinetic energy. This is the potential energy as a function of position. And one interesting problem might be, where is my position where the potential energy and the kinetic energy are equal? It's not halfway. If you look halfway, it's not even close. It's over here somewhere. So that'll be an interesting problem for you to think about. Okay. We can also think of the energy as a function of time. And rather than redraw it on here, I'm going to show it in the book, because it's just, the book does a much better job than what I can draw. And here's the magic of the document camera. I really want you to study this figure 1510. Here's the energy, and now we have time here. Now these are going to be multiples of the period. But this graph makes so much sense, but I want you to study it. At t equals 0, let's suppose that we're starting with that we're starting at the maximum displacement. Well, at t equals 0, I'm starting at 1/2 Ka squared. I'm starting at x equals a, and I'm releasing it. Now what happens is this. Let's look, just look at the potential energy. The spring moves towards the equilibrium position. Therefore, it loses mechanical energy until it reaches 0. I mean, we lose potential energy until we reach the very center, and then we go back out on the other side. And then we lose it again, but this is half a period, and then another half a period is a full period. Well, let me actually go back to this. Let's look at oh, that's right, because I moved the camera. U as a function of time now is equal to 1/2 kx squared, but x squared is a squared cosine omega t squared. So this is all a constant. So really what we're graphing is a cosine squared function. Now this is never negative because it's squared. Everything here is positive. So there's no such thing as negative potential energy in this problem, unlike gravity where you can have, but on a spring it's always positive. Okay, well, what about the kinetic energy function? K is equal to, well, it's 1/2 mv squared, but v squared is a squared omega squared times sine squared omega t. And this stuff right here is just all a constant. And actually it's the same as this. This reduces to 1/2 ka squared because omega squared is k over m, so the m's cancel, and you get 1/2 ka squared. So the kinetic energy function as a function of time is a sine wave, is a sine squared wave, and the potential energy is a cosine squared wave. Okay, and now to visualize this, let's visualize this in terms of time now. Here I have my object out here, and here it is at the minimum, maximum, minimum. Now, think about this in terms of potential energy. It's at a maximum right here, right? Now, let's think of this in terms of the period of a complete oscillation. How much time does it take to go back and forth? 1 period. So you can, and this is all very symmetrical, isn't it? So the time it takes to go from here to here is 1/4 of a period. From here to here is 1/4 of a period. From here to here is 1/4 of a period. And from here to here is 1/4 of a period. So in the first fourth of a period, the energy, the potential energy, starts at a maximum, goes to 0. The next fourth of a period, it goes from 0 to its maximum again. From its maximum back to 0, from 0 back to its maximum. So in other words, it makes 2 complete oscillations in terms of energy in 1 period. And that's what this graph shows right here. It goes from here to 0, back to its maximum on the other side. Back to 0, back to its maximum to where it started. Now it's back to where it started, and that takes 1 period to do. And this is a cosine squared function. This is a sine squared function. Here's the kinetic energy. It starts at 0, goes to its maximum. Now it's at x equals 0. And then it goes back to 0. Now we're half a period back to the equilibrium position at maximum kinetic energy. Back to 0. We're back where we started. Okay, I really want you guys to study this. This is, and I've seen this graph on the AP test, especially on multiple choice. But it's really interesting, and it really makes a lot of sense. So study it, think about it. Now, finally, I want you to look at this figure. This is figure 1511 in the book. And it's rather complicated to draw, so I'm just going to use the book here. But here we're starting at t equals 0. We're starting at our maximum displacement away from the equilibrium position. Here's the equilibrium position right here. And they show all these different quantities: time, position, velocity, acceleration, kinetic energy, potential energy. What are they at the different parts of a single oscillation? Well, here we're starting at time t equals 0. The position is A. The velocity is 0. The acceleration is at its maximum, which is negative omega squared A. The kinetic energy is 0. The potential energy is at its maximum, 1/2 k squared. Then we release it. It accelerates here until it's right here. We're through a fourth of a period. The position is 0. We're at maximum velocity, negative omega A. The acceleration is now 0. Why is the acceleration 0? Well, let's look at the forces. The spring is totally relaxed. There's no net force on it. So there's no acceleration because there's no net force on it. It is moving, however, so it's going to keep moving. And all of the energy is kinetic and 0. And then we get to maximum compression of the spring. We're now halfway done with our cycle, half a period. Our position is at negative A, 0 velocity, and these guys, this is omega squared A, is our acceleration. Now it's positive. It's shown by this arrow. And then we move here. Now we're 3/4 the way done with our cycle. And now we're completely done. And then it just starts over again. Study this. Really understand this. And if you understand it from the point of view of, time, position, velocity, acceleration, kinetic, and potential energy, you really understand simple harmonic motion and what's going on. It's very cool. Okay, that is it for the lecture.